Right, so welcome to Math 383. This is, I think, lecture 17. Hopefully my counting is not off. So what I want to do today is I want to do, again, more review of analysis. And my goal is to try to move some of the more standard material to just having you read it in the book, watch the videos, and then if you have questions, ask me. Happy to meet with you privately, happy to meet with you in groups, happy to use some of class time to discuss this. But I want to try to use class time effectively. So there's going to be certain topics that I will move entirely online because you can do that very easily with complex. There's whole segments you can just pull out of the course and just say, look, it's great to know this if you're going to go to grad school. If you're not going to go to grad school, there's other things that are more important to focus on. So, again, you have to let me know how things are going, what you want me to be covering, and what you are fine with. So I want to talk today about logarithms. And one of the reasons I'm doing this is because based on, I'll try to phrase this diplomatically, based on how strong your real analysis and multivariable calculus is, I of course have no doubts as to how well you were taught in high school and junior high. And I would just love to feel good about education in this country by seeing how well you know these concepts. You've got to be very careful when things are being recorded. Right? Can anybody answer the most important question you have in a class, the who gives a shit? Why do we care about logarithms? Can anybody give me a reason why we care other than it's in the curriculum, other than my professor cares? Why do we spend time learning logarithms?
They're useful to linearize.
Yeah, excellent. They're useful to linearize. The whole point of differential calculus is that locally, every nice differentiable function looks like a line. We understand lines. That's one reason. There is another reason why we care about logarithms. Yes? It is nice to have an inverse to the exponential function, but why do we want to have something like that?
If you have x in the exponent, it can give you an answer for x.
Yep. Oops, let me just. Hello? Oh, okay. I'm sorry, I have called at several different hospitals all over New England to try to get an appointment for my daughter. And December and January is the earliest ones we can get out, other than the November one in Pittsfield. So what is true about the exponential function? When you think about its properties, what do you think of when you look at its plot?
It's too, like it increases.
It increases very rapidly. So the advantage of the logarithm is there's this nice one-to-one relationship between numbers and their logarithms. It allows us to look at things that span many orders of magnitude. So here's a beautiful picture of the sun, and there's the Earth, and that really is the moon, drawn to scale over here. It's not some smush on my slides or the screen. Okay, when you want to try to see something like this, can you imagine now drawing, a human being? Or a baseball? You can't really see things that are this many orders of magnitude. The other one which was mentioned is linearizing. So here is a plot of the 100 most populous cities. If I take a log-log plot, all of a sudden, I now have something that looks a lot like a straight line. Okay, can anybody give me situations where you've seen logarithms? And I've got a few that are later. I'm sorry? Right, but I'm saying, where in the world have you seen logarithms? Chemistry, where in chemistry? pH levels. pH levels. You might also see in some of the concentration problems. Where else? Richter scale. An earthquake that's an 8 is 10 times an earthquake that's a 7. Okay, so just to make sure we're all on the same page, I found out this morning that when I tried to transfer the slides to the program that Apple uses, all of the subscripts no longer became subscripts. And so I've just taken screenshots. So then rather than advancing everything, I'm just going to shove everything all on one slide so that I would much rather see the subscripts and exponents come up correctly. So if x equals b to the y, then the log of x base b is y. That's the definition. We normally use base 10 when we're doing data in a lot of scientific studies because we have 10 fingers, but we really, if we're doing calculus, want to use base e because then the derivatives are nice and you don't have to remember where is that fact of the log of b in the derivatives. Computers also like to use base 2. It's very convenient for what they're doing. All right, I'm going to assume everybody is familiar with the basics of logarithms. As was mentioned, they allow us to compare on one plot many orders of magnitude. So we go from the radius of a proton at 10 to the negative 15 meters to the radius of the visible universe, 10 to the 26th. So this is a little bit over 40 orders of magnitude. You know, it's just mind-blowing to think about that much of a difference in size and scale. You know, as mathematicians, we're used to just manipulating quantities without really stopping to think, what is it? Okay, you want to try to find a way to visualize and explain and understand things of this order of magnitude. Well, when I put it on a log scale like this, I can now all of a sudden talk about all these objects simultaneously. All right, so as was mentioned, you know, we have the Richter scale for earthquakes. You know, if you really care, you can look at some of the big earthquakes in the past. Decibels, nobody had mentioned. This is another one. It would be interesting to plot the volume of certain math professors on the decibel scale. You might have conjectures as to who would win. Actually, might not even be a conjecture. We have the pH scale from chemistry, which was mentioned. And then as was mentioned, it's the inverse of the exponential function. So on the left, I'm plotting exponentials in base 2, e, and 10. I think we all agree these are the big three. Oh, I'm sorry, this is Williams, we should do the little three. Yes. And then on the other side, we have the exponentials. I'm sorry, the exponentials here, and on the other side, we have the logarithms. Now, when you try to look at this plot, the 10 to the x, I can't even show you where that is at 3 on the same scale. The growth rate is just phenomenal. And when you're trying to look at things, it's a real challenge. One of the best quotes I've ever heard about complex analysis is, it would be so much easier if we could actually visualize the plot of a complex function. You have a two-dimensional input and a two-dimensional output. Good luck. We can play games with color and whatnot, but it's not the same. We can plot the absolute value of the function, but it's not the same. All right, so we've talked about many orders of magnitude. What I want to talk a little bit now is linearizing many nonlinear functions. And so here, I'm going to plot x to the 0.25, x to the 0.5, x squared, and x to the 4th on the left. I think everybody can see x to the 4th. With a little bit of work, I think you can see x squared, the green line on the bottom. And that's about it. I can't really see the other ones. And just plotting just x squared and x to the 0.5, I can see them, but there's a tremendous difference in magnitude. And as x gets larger and larger and larger, it's going to be tremendously difficult to really see what's going on. If I take logarithms, it's very different. And so there's the semi-log plot and there's the log-log plot. And so if I just do a semi-log plot, I'm going to still plot the x-axis as normal, but the y-axis is going to be the log of the number. And I can now see all 4 functions. And if you look, they seem to be growing slowly. Well, this is a common feature of the logarithm, but this is only going up to 10,000. If I do a log-log plot and I plot the log of my function against the log of x, I can go up to 10 to the 455 without any trouble. It's mind-blowing to think about something of the size 10 to the 455. I've got a bunch of physicists here, correct? How many subatomic doohickey thingamabobigs do we have in the universe, roughly? How many items do we have in the universe? 10 to the 80, 10 to the 90, somewhere around that range. Let's round up to 10 to the 100. So imagine every subatomic speck in the universe was an entire universe. How many objects would we have? 10 to the 100 objects in the universe, and every one of them was a universe. How many objects would we have? 10 to the 200, all right? I'm plotting at 10 to the 455. That should give you a sense of just how vast this number is. But we look at it on a scale like this, and it doesn't seem that bad. You've got to be very careful in terms of looking at things. For some things in math, things converge on a logarithmic scale. So we have no hope of going far enough. How many people are in Dance of the Primes? There are some things that we believe kick in around 10 to the 350. So in terms of how far you would have to go to start to see some of these things is just beyond what we are going to be able to do for a long period of time. But logarithms allow us to talk about a lot of these things. Okay, hopefully everybody remembers the exponential laws. Your bm times bn is b to the m plus n, bm over bn is b to the m minus n, bm to the n is b to the m times n. Yes, these should all be, and very similar to calculus, every rule of differentiation leads to a rule of integration. What is the rule behind the integration rule, integration by parts? Product rule. What is the rule behind U substitution? Chain rule. So you give me a differentiation rule and I can recast it as an integration rule. So similarly over here, I can recast these powers of exponents as logarithm rules. And so the big ones that we have, let's move this out of the way, is the law. Oh, come on, it didn't change. All right, hopefully the other ones changed. All right, so in some places, the ones and the twos are no longer subscripts. They have now been upgraded. They're now flying first class. So you should still read it as x1 and x2, but that really is x times n. Wonderful. All right, so the log, oh, no, that's x to the n. No, that is x to the n. Oy. All right, so the log of x to the n is n times the log of x. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And then the last, the most forgotten, is the change of base formula. The log of x base b is the log of x base c over the log of b base c. The reason this was so important in the old days is that you only needed to know logarithms in one base. Once you knew them in one base, you knew them in every base. How many of you have taken a good stats class? I knew there was an issue as soon as I said good in front of stats. How many of you have taken a stats class? Okay. Okay. When you took a stats class, did you have a textbook? Did the textbook have a table of values of your probabilities from the normal distribution in the back? Which normal distribution did it have? Yeah, 0 1, the standard normal. Why didn't it have other normals? Because you could just scale and convert. And so you only need one. That's the power of the change of base formula. We only need to know logarithms in one base. And once we know them in one base, we know them in every base. Now, for convenience, you might have logarithms in several bases because I'm doing things in base 10. I'm doing, physics, chemistry. I want those values. Or I'm doing some calculus and I want to have something that's nice and differentiable. So I might want to have base E. I might want to have base 10. I might want to have base 2 for my computers. So it might be convenient to have it in multiple bases, but I really only need one. There's a really good math concept here. And again, I was talking to some people at breakfast today about trying to extract key things. How do you look at things? We are lazy. Mathematicians are lazy. This is a source of pride. You want to reduce things to something you already know. Okay? I'll risk telling this joke. A mathematician and an engineer are walking down the street and they see a house on fire and a hose disconnected to a hydrant outside. Who here has heard this joke? Okay, so you can tell me if I start going down the wrong path. So the mathematician quickly connects the hose to the hydrant, turns it on, puts out the fire. They keep walking down the street and they see another house, which is fine, and a hose connected to a hydrant. What does the mathematician do? Yes. Lights the house on fire and disconnects the hose, thereby reducing this to a previously solved problem. And continues walking down the street as the engineer shakes his head in disgust. Right? Mathematics is all about reducing things to things you already know. If I know how to do this, I just try to convert it back to something I already know. That's my go-to. When we're trying to prove these log laws, you actually don't need to prove all of them. If I prove the first and the second, if I take n equals -1, then the third is a function, is a consequence of the first two. So you can always ask, what's the minimal amount of work I need to do to prove something? I try to reduce things as much as possible to calculations I've already done. Okay, so let's go through the proofs. And so the first one we'll prove is the log of x to the n is n times the log of x. And so this is very similar to all the differentiation results you've seen. So how do we prove differentiation laws? Well, let's let a of x be f of x times g of x. We write down the definition of the derivative, and then we multiply by 1 or we add 0 and do something in a clever way. So over here, the log of x base b equals y means x equals b to the y. Now that I've converted this to something that's an exponential, I know laws of exponents. So now I use my knowledge of laws of exponents to solve and prove my log results. So I'm trying to reduce to something I already know. This is why I'm spending time today going through this. This is the high level, how do we attack problems? So then x to the n is just by to the n, that's just b to the n y. Oh, okay. And now by definition, with a little scratching, we get the log base b of x to the n is just n times y, but y was just the log of x base b, and there's the proof. So that's the proof of the power. If I now want to do the sum, it's interesting, sometimes it worked, sometimes it didn't. So I want to say the log of a product is the sum of the logs. So we start off, as always, we just write down definition. What does it mean for the log of x1 to equal y1? That means x1 is b to the y1, and similar for x2. So now we just multiply x1 times x2 because I want to study the log of x1, x2. So again, try to take the object you want to study and break it into things you understand. And now we use the exponent law. The product of two exponentials is the exponential of the sum. So b to the y1, b to the y2 is b to the y1 plus y2. And now by the definition of logarithms, the log of the product is just going to be y1 plus y2, and I substitute. Okay, next one is the log of, which one am I doing? The change of base formula. So this one is a little bit more involved. So if I have the log of x base b is y, that means x equals b to the y. What makes this a little bit easier is I'm telling you a little bit about what's going on. I want to change things to a different base. I want to change things, and I want to study things base c. Well, I can write x as c to the u and b as c to the v for some numbers u and v. And so now this allows me to convert from writing x in base b to writing x in base c. If x is equal to b to the y and b is c to the v, then I get x is equal to c to the vy. And so there again, some typo in terms of how it's writing. So I will fix that to c to the v times y. Okay, but we also know x is equal to c to the u. Well, if c to the u is x and c to the vy is x, then we know u has to equal vy, or y has to equal u over v by division. And so now when we just substitute, we now get the log of x base b is the log of x base c over the log of b base c. So if we know logarithms in one base, we know logarithms in every base. This is not used that often because nobody uses tables anymore. Computers just have this all stored for you. There is one place where we do use this. If we want to take the log of x base b and take its derivative, well, if we take c to be e, then we can now take the log base b is the natural log of x over the natural log of b. I know how to take derivatives of the natural log. And this is how you would get the derivative of the log of x base b from knowing the derivative of the natural log. So that's one place where we do use the change of base formula. And again, I just wanted to do this because this chapter is on the complex logarithm. What do you think would be good to know before you do the complex logarithm? The real logarithm. And so given that it might have been some time since those excellent classes in middle school or high school on the logarithm, I thought it was worth taking a few minutes and just quickly reviewing properties of the logarithm, how do you prove them, and why do you care about them? Now, in complex analysis, we're going to get a completely different reason to care about the logarithm. This is not a reason you would have expected when you were doing algebra 1, algebra 2. This allows me to integrate, what the hell does that mean? Okay. Okay. Any questions about logarithms so far? To just give an example of how logarithms can help, here's the factorial function. It's the number of ways to order n objects when order matters. So n factorial is the product of n all the way down to 1. I just wrote a quick Mathematica code, and I will send some links later today about how to do some simple programming in Mathematica. If you've never done that before, I've got a tutorial on how to use it. Mathematica has a lot of very nice predefined functions which make the analysis easy. There's a problem I've been discussing with some people in the class. if there's some time at the end of today, I'll talk about it, but I'll send some code about how you can write a mathematical program and get some intuition as to what the answer should be. And that's the level of coding you need to be able to do. You do not need to be a professional writing 10,000 lines of code, but you've got to be able to write, say, 10 to 50 lines of code and gather some data and get a sense of what the answer might look like, and that can help influence your analysis. And so when I'm plotting the factorial function, I love the first one. The first one is the normal plot, where I'm just plotting the factorial function, and you can see it's essentially 0, and then it just shoots up. And it's really tough to see things on a natural scale. The next is a semi-log plot. So I'm plotting n is the x-axis, and the y-axis is just the log of n factorial. And then the next one is a log-log plot. If you look at this, Stirling's formula, which we will prove later in the semester, n factorial is about n to the n e to the minus n square root of 2 pi n. So when you take the logarithm, the log of n factorial, oops, that's missing, is about n over e log of n. Well, the log of n is very slowly growing. So what this is telling you is the log of n factorial is almost some constant times n over large regions. And this does look approximately constant, in terms of slope. But if you look really closely, it does look like the slope is maybe ever slowly growing. But this gives you some power in looking at, yes.
Oh, that's okay.
Okay, in terms of looking at functions and getting a sense of what's happening. I can now look across many orders of magnitude. Now, yes.
So should it not be log n factorial is approximately n times log n over e instead of n over e times log n?
Did I make a mistake? Let's see. It should be, so n factorial is approximately n over e. I might have made a mistake. N over e to the n times 2 pi n to the 1/2. So I take the log of n factorial. That's going to be approximately n natural log of n over e. Right?
Yes.
Plus 1/2 natural log of 2 pi n. Oh, so yes. So this should be, yes, the natural log of n over e. Thank you.
Oh, and then
And then that, the mistake was the e, right? Yes. So then this should be approximately n times the natural log of n over e. Yes. Thank you. Now, I told you mathematicians are lazy. Mathematicians are also really good at recognizing patterns. So when you look at Stirling's formula, is there any part of it that jumps out at you as a nice quantity? Square root of 2 pi, right? Where have you seen square root of 2 pi? I'm sorry? So one is Fresnel integrals, and in fact, the Fresnel integrals is not the first place you would see the square root of 2 pi. It's related to the Fresnel integrals. The Gaussian. So is there a Gaussian lurking here? Yes, actually. And that's where the square root of 2 pi is coming from. It's giving us a hint that there might be a Gaussian lurking in the background. Where else have you seen a 2 pi? Yeah.
Like a circle, but not a radius.
Right. But in this class, where have we seen 2 pi?
The integral.
The integral formula, 1 over 2 pi I. So could the 2 pi be coming from that? So the problem is there's lots of places a 2 pi can come from. It can come from, as you said, the perimeter of a circle, which is related to the 1 over 2 pi I we have when we do contour integrals. It's also coming from the normalization of a Gaussian. Is that related to a contour integral? But you want to start thinking about patterns. The more patterns you have, the more ideas you have of how to try to prove something. Okay? All right, I don't want to say too much. Oh, interesting. So it was multicolored before, but somehow the colors were lost when it went. All right. So I will try to make this colored. All right, so I don't want to go too much detail right now about simply connected and stuff like that. I'll let you look at the book. What I'm looking at here is a space that's not simply connected. It has a hole in it. So if I give you, two curves, connecting, say, 2 points, and maybe here is, gamma 1, and here is, gamma 2, can I pass from one curve to another? And over here, if you look at what's going on, when t equals 1, I have the curve gamma 1 of t. And when t equals 0, I have the curve gamma 2 of t. So this is a way to pass from one curve to another. And if you can pass from one curve to another in the space, then you can often show that the integral over one is the same as the integral over another. So for example, frequently I might give you, some space like this omega, and I have, my 2 points, and I have here, one curve like this, and I have another curve maybe like this. And what I can do is I'll have, a string of curves moving from one to the other. And then what I can do is I can draw lots of small little balls. And if I look inside one of the small balls, just zooming in, what we can do is we can, play the games with Gorsat's theorem, Cauchy's theorem, all that stuff, and say, look, I can show that the integral over the green is the same as the integral over here by just, drawing some small little triangle like this. And as I keep marching down, I'm going to have this going in both directions. So it's going to cancel out. So I can just do these little tricks and go from one to the other. And so integrating over the outside green would be the same as integrating against the first gold next to it. And I just keep passing from curve to curve to curve. And then this is where you have to now be careful with your bookkeeping. And it would be wonderful if we had some kind of results that, I don't know, maybe finitely many open balls would cover the set. Wouldn't that be a nice result to have and reduce things to a finite problem? And you can begin to see now why we care about all these results from analysis. And then we pass from one thing to another. But we need to have everything holomorphic in that region. If I have a big gaping hole like this, I can't pass from one to another. You can make all of this extremely rigorous with a lot of topology. Yes?
What are you talking about an X curve?
Well, there would be infinitely many curves. But what you could do is you could look at some discrete set. I could look at maybe a discrete set of t. T is 0, 1 over n, 2 over n, 3 over n, something like that. And then I could have maybe a sequence of finitely many curves. And then the hope is that if I choose my partition to be sufficiently small, then I can use compactness up the wazoo, that's a technical term, and just show that I can pass from one to the next, to the next, to the next, to the next, and it's a finite process, and I'll get to the blue curve at the end. So we could make this extremely rigorous. We could have a lot of topology coming in, or we could basically just say, we're going to accept this and move on, and that everything we look at in this class is always such a nice space that we don't need to worry about this. We're integrating over semicircles, we're integrating over straight line segments, we're integrating over either disks or annular regions where someone has punched out the center. In all of these, we understand what's going on. So rather than proving the theorems in the greatest possible generality, we'll just say that our friends, the topologists, have a use. Okay, and they give us theorems. And we use those theorems to then say that, yes, we can do this over any curve. But for this class, we will just say, yeah. Okay? And so the next thing is the notion of a branch cut and trying to define where things can be constructed. So if I give you the exponential function, I want to try to find its inverse. It's very easy to exponentiate. And the reason it's easy to exponentiate is we have a formula. You give me any z, and I can expand e to the z as a power series that converges for all values of z, no problem. How do I find the inverse function? So we saw plots of logarithms earlier. What can you tell me about the output of the standard logarithm function? What can you tell me about the output of the logarithm? What kind of values?
The single value function.
Single value function, but what kind of values could be the output of the logarithm?
Like
Negative infinity to infinity. What about outputs of the exponential function? Non-negative. We can't get a 0 as an output of the exponential. So if I want to take the logarithm of the exponential, that should return myself to the starting value. But I should be a little bit afraid about taking the logarithm of a negative value because I can't have the exponential of a negative value. So let's consider, so I seem to have lost things. Okay. So if I give you, z equals x, then the log of z would just be the log of x if x is greater than 0. This is just a standard, yes.
Well, maybe also like is the log almost more natural in complex numbers because everything has a positive magnitude.
So now let's take that suggestion. Let's write z as r e to the I theta, and let's define the log of z. It's going to be the log of r plus I theta. That seems like a very reasonable definition. And I'll put this in quotes as this is a provisional definition. This reduces to the standard definition if z is a real number. The difficulty is what happens if, let's say I start off with a value over here. Then the log of 1 is 0. And then I start moving around like this. And maybe I swing around in crazy ways. And I start coming up like this. Well, the problem is here, theta is getting closer and closer to 2 pi. And so as I come back and I get closer and closer and closer to returning to 1, I would now be getting the log of 1 equals 2 pi I. So we would get the log of r e to the 2 pi minus epsilon I theta is equal to the log of r plus 2 pi minus epsilon times I. And as we get closer and closer and closer to 0, I'm sorry, it's epsilon equals 0, we're now getting closer and closer and closer to the point 1. And we now have 2 different values for the log of 1. So the difficulty is we can write 1 in multiple ways. Then you might say, well, why don't I just write 1 as 1 times e to the 0? The problem is, as I walk around like this, my theta is increasing, and I can't have my theta discontinuously fall to 0. So this is why the logarithm becomes so difficult to define. Because if we try to walk all the way around, we have an issue. And so one of the solutions is what's called a branch cut. And so the most common branch cut is we take 0 and we throw away the negative axis. And we remove this. This is our branch cut. And so we're not allowed to cross the negative axis. So now, if I start to try to wander from 1, I can wander, but I can't get below. And so I would have to swing around. I could come up like this, I feel, and I swing back to 1. And now if you look what happens, as I start wandering towards the negative axis, my angle is getting closer and closer to what? Pi. And then I walk all the way back and my angle becomes 0. And now as I walk to the negative axis from below, what does my angle start going to? Negative pi. And then when I come back to 1, my angle goes back to 0. And so if I have this cut like this, and if I do not allow myself to cross that line, then I can define a logarithm. Now, you could, of course, become more exotic if you wish. I could define, for instance, maybe some kind of branch cut like this, spiraling around like this, going off to infinity, and say, I'm going to throw away this from the complex plane. And if I do this, you're never going to be able to walk all the way around. That's what we're trying to prevent. You walking all the way back to where you started and having the angle change by 2 pi. When I throw away part of the complex plane, I'm doing it in such a way that I can't loop back to where I began. Okay, so I'm not going to go through the proof in the book. It basically says, suppose you have a simply connected region where you have 1 in omega and 0 is not in omega. Without loss of generality, this is basically saying, look, let's just adjust things so that 1 is in omega and 0 is not. So there's got to be at least one point that's not in your space. And we're just going to adjust that to be the point 0, and we're going to take one of the points to be in the space to be 1, just for convention, just to normalize things. We can define a branch of the logarithm such that we get a function f that's holomorphic. E to the f of z is z, and whenever z is a real number, f of r is the log of r, is the standard logarithm. So there is a nice way to generalize all of this. And this is the the calculus we've seen before. The integral of 1 over t is the natural log, or the exponential of the logarithm is x. Yes.
The theorem says wherever r is a real number and near one, why do we need the near one and how near?
Well, because if r gets close to -1, for example, or -5, the logarithm is not defined. The standard logarithm is not defined for that.
So just near enough for
Near enough to 1 that we're away from 0, we're away from the branch cut, then everything is going to be well defined in a group. But if we go too far away, all of these results are always local. Locally, near this point, things are good. As you start to get too far away, all bets are off. I'm not telling you what kind of cut I'm having. I'm not telling you what omega is looking like. I've got to be very careful. I'm only making a claim locally. Okay, and so the way the proof works, and I'm going to again leave you to read this, is you construct f as the integral of little f, where little f is just 1 over z. So essentially, you do what you did in calculus. So you can define the natural logarithm to just be the integral of 1 over t. That's a perfectly valid definition. You then show that this has all the properties of the natural logarithm. So if you start off with the natural logarithm defined as the inverse of the exponential, then all these properties are obvious. If you define it as the integral of 1 over t, it's not as clear. And so we just show that this is well defined and that this is independent of path. So the independence of path is the key observation. And that's where we need the simply connectedness so we can deform one path to another. If we have holes, we can't deform one path to another. And that's why it is absolutely essential that the region is simply connected. Okay, and so as I mentioned over here, you could have these terrible spirals. The color seems not to have come in, so I will put in red over here. And so if I throw off something like this, going off to infinity, if I try to do this blue squiggly path, is there a danger as I come around here? Well, I can't quite get back to 1. And so because this blocks me off, this is not a proof, right? This is meant to just give you some intuition as to what's going on. Because of the way this is winding around, I can't get back to 1 unless I retrace my steps. And as I retrace my steps, my angle goes back to 0. Okay, I'm not going to prove this, but if you have a function which is nowhere vanishing and holomorphic, then you can, in a simply connected region, then you can always write it as the exponential of a holomorphic function. So one of the big things we're going to be looking at, we're going to skip chapter 4, we're going to go to chapter 5 on products. If I tell you where a function is 0, how much do I know about the function? If I know all the places it vanishes. I can't know the function completely. Why can't I know the function completely? If you know where the function is 0. Yes?
You can scale it.
Yeah, I can always scale it. And then the question is, could I multiply it by something that's never 0? Yes. And so unfortunately, there are infinitely many things that are never 0. The exponential of any holomorphic function is holomorphic and is never 0. So if I tell you the zeros of a function, that's not enough to uniquely determine it. It only determines it up to an exponential of a holomorphic function at best. Now, in real analysis, I can give you the zeros of a function, and there's lots of strange things I can multiply by. So it's a really difficult problem. So if I know the zeros, I want to figure out what's the maximum amount of information I can deduce about the function. Okay. Again, I'm not going to go through the proof. I've just got some notes here on the slide. And then just, for definiteness, just so the slides are complete, I've just pasted the proof from the book. It's pretty straightforward. The key idea is we guess what the the definition of the logarithm is, and then we show that it works. And then once that you have that it works, then you show that it has the properties that you want. So this is method of divine inspiration. Okay, what I want to do now for a couple of minutes, especially since one of the homework problems involves the sine function, is I want to show how you can redo all of trigonometry by knowing complex analysis. And if I really wanted to, I think it takes about 1 minute to prove everything. Yeah, I don't think I really want to rush myself, so I'll go a little bit slowly. But let's start off with, e to the z is the sum, n goes from 0 to infinity of z to the n over n factorial. And then e to the I x is cosine x plus I sine x. And this comes from, if I want to look at the Taylor series of cosine, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 dot. And then you can just see if I plug in ix for z, when I expand everything out, things are going to be very, very nice. Now, what we really want to have is the following theorem. E to the z, e to the w is e to the z plus w. If this is not true, then whoever created this notation should be shot, right? Because when you see this, when you see e to the z times e to the w, is it just e to the z plus w? No. What is e to the z times e to the w? What is e to the z times e to the w? No. I'm sorry? It's the product of the Taylor series. It's the sum, n goes from 0 to infinity of z to the n over n factorial times the sum, m goes from 0 to infinity, w to the m over m factorial. That's what it means to have the product of two exponentials. Now, you can show that this is the same as the sum k goes from 0 to infinity, the sum L goes from 0 to infinity of z to the k w, oh, sorry, z to the L, w to the k minus L over L factorial k minus L factorial. So first you have to show that I can reorder the sums. This is the Fubini theorem. The sum of the absolute values converges. And then what I'm going to do is when I multiply everything together, I can look at the product of the z's and the w's. And I'll group all the terms where the sum of the exponents is 0, then all the terms when the sum of the exponents is 1, then all the terms when the sum of the exponents is 2. So if I want all the terms when the sum of the exponents is k, if I have L powers of z, I need to have k minus L powers of w. If you are very, very quiet right now in hunting rabbit, you can hear something. There's something that's missing from this expression, that it's screaming, it wants to be there. It wants a k factorial. So let's just put in a k factorial because we like to. Can we do that? So we divide by k factorial. And if we do that, I'm just so excited. What is this piece over here equal to? It's a binomial. It's just k choose L. So then this becomes the sum, k goes from 0 to infinity, 1 over k factorial. Then we'll have a sum, L goes from 0 to, oh, it's not 0 to infinity. This is 0 to k, sorry. 0 to k, we will now have k choose L, z to the L, w to the k minus L. What is this quantity in brackets? It's z plus w. So we just get z plus w to the k over k factorial, which is e to the z plus w. This is what you need to do to prove that the product of the exponentials is the exponential of the sum. Now we have that though. Okay. Any questions about this? How many of you have never seen this before? So this is what you need to do to rigorously work with the exponential function. But now we have it. So now let's do all of trigonometry. We've got 5 minutes, not even going to be close. So e to the I x is equal to cosine x plus I sine x. So what is e to the ix times e to the minus ix? E to the 1, it's just e to the 0, which is 1. So we get cosine x plus I sine x times cosine x minus I sine x equals 1, which is the same as cosine squared x plus sine squared x equals 1. There's Pythagoras. Let's do e to the ix, e to the iy. This is what? E to the ix plus y. So cosine x plus I sine x, cosine y plus I sine y is cosine x plus y plus I sine x plus y. Well, this is the same as cosine x cosine y minus sine x sine y. I'm just taking the reals together, plus I sine x cosine y plus cosine x sine y. So this must be the same as this. This must be the same as this. There's your angle addition formulas. All the trig you want, you can now get because you know the exponential function. We can go and check and see just how long it took once we had these prereqs. It might have been 2 minutes. We were doing it at a casual pace today. All your trig identities. Once you remember the exponential, e to the ix, e to the minus ix is just 1. And then e to the ix, e to the iy is e to the ix plus y. Everything follows from that. If you want to do your n angles or your half angle formulas, you can get them from this as well. So as a nice exercise, try to get the half angle formulas. So it's amazing how many things you get once you understand the exponentials. There's tremendous dividends from this. But we would not be able to do this if we didn't have the fact that the exponential, so the product of exponentials is the exponential of the sum. So that is absolutely crucial. And to do that rigorously, we actually do need to know a little bit from either multivariable calculus or real analysis about switching the order of summations. We're really changing variables. And rather than summing, in one way, we're now summing over like triangular slices or something like that. So I strongly urge you to go through this proof and try to just make sure that you understand what's going on. For the last couple of minutes, I want to just switch to leading into the Weierstrass products for next time. So much of math is about trying to solve equations. If I give you a linear equation, ax plus b equals 0, I'm pretty sure everybody knows that the roots are just x equals negative b over a. If I give you a quadratic, it's not that bad to find the roots. This is the beautiful quadratic formula. And maybe next class with some time today, I'll talk a little bit about how you find the quadratic formula. There is a formula for the cubic. There is a formula for the quartic. And by a formula, I mean a nice formula involving just the coefficients of the polynomial. I can write things down very explicitly. In general, however, there is no formula for quintic and higher. So we have to do numerical approximations. So here is the formula for the 3 roots of the general cubic. What could you do to try to make this a little simpler? What kind of adjustments could you do? Without loss of generality, we may take, yes. Yeah, you could take a equals 1, just pull out a. And you could make b equals 0 by translating the roots. So you can always make the second highest degree term have a 0 coefficient. So that would make this formula a little bit easier to memorize, but it would still not be pleasant. Here is the formula for the quartic. Or actually, this is just one of the roots. It's getting worse. There is a reason why you weren't memorizing these. Okay. And so what we're going to want to study, and we'll do more about this next time, is what if I give you finitely many roots? What can we say about that? What if I give you infinitely many zeros? What can we say about that? All right, so this is a good place to stop.